exciting to read. Okay, well, according to my clock, it's 2 o'clock anyway. The clock in the room begs to differ. This is what we'll be talking about the coming 5 weeks, and I'll just keep filling the time with stuff that's available. I hope that it will fit what I have in mind. Permutation models, what is that all about? Well, we will see as the weeks progress. There's something with permutations in there, and there's also something in there that was probably discussed in the first few weeks, maybe as an aside, but we'll be using them a bit more explicitly. And that is something called set theory with atoms. Those are, how shall I say this, sets that are minimal in the epsilon relation, yet they are not empty, because we simply stipulate that they're not equal to the empty set, which sounds a little bit strange, but I'll write down the axioms in a moment, and from that I think most of the things will follow. Why set theory with atoms? Well, this was historically the first time that somebody was able to show that the axiom of choice, the well-ordering theorem, is not actually provable on the basis of the other axioms. Okay, the axiom of foundation wasn't there among that list. But anyway, Fraenkel and Mostovsky are among the first who developed this idea to show that you could have situations, at least, where the axiom of choice wasn't valid. And what was the idea? The idea was basically take some atoms and make them indistinguishable by means of the permutations, make them so indistinguishable that you could not find a well order anymore. The set was so homogeneous that it was impossible to pick out the first one, the second one, the third, and so on, so as to create a well order. Of course, we, from the outside, looking at those atoms, could say, well, we have the well-ordering theorem, there is a well order, but the point is the well order wasn't available in the model, and that's all. That will all become clear, I hope, in the coming weeks. So what does set theory with atoms look like? Well, so this will come later, but we need to do this first. What we do is we take the language of set theory and we add 2 constants to it. We do have to add a specific constant empty set to it, because otherwise it wouldn't appear. And we have to distinguish it from the atoms. That's why we name it explicitly. And what we will do is we will try to keep as much of ZFC as possible, but we have to cater, we have to do something for the atoms. And so, for example, we explicitly tell ourselves that the empty set, yes, doesn't have any elements. Fine. So actually I should label that axiom as the empty set, because the next axiom is about A. What about A? What are the new axioms about A? Well, I think we should also probably, well, no, it's there explicitly. So A, the constant A, refers to a specific set in our universe. And the axioms tell us about the elements of A that they are not equal to the empty set. We simply say it is not equal to the empty set. And but it does have this property with the empty set in common.
Do we still have extensionality?
We'll get to that. I mean, the except isn't done yet. At some moment I will say, and these are the exceptions. But, so we have the normal axioms of ZFC, except, well, first we add two things. You know, in normal ZF, you could prove that there was an empty set by using the separation axiom. But now we have to distinguish, we have to make a distinguished element that is going to work like the empty set. And we're going to have some other distinguished elements that are not the empty set and are still indivisible, so to speak. They don't have any extra elements. And the question here was, what do we do with extensionality? Well, we have to modify extensionality. So extensionality, here we go, is formulated only for the things that are not in A. There is actually, let's see, so what you could think of is that you could create an extra predicate called set, and set just means not an element of A. Okay, and I'm not talking about classes, but just all the individuals that we talk about, as soon as they're not elements of A anymore, they're normal sets.
And why don't we do that with A? So why do we make A a constant rather than a unary predicate? We say, well, is there a reason, or is it just
no? Because actually, no, we want A to be a set. if we had said A was a unary predicate, it could still be a proper class.
Yeah, and then, so that we will run into trouble.
Yeah, but then we would have to say that A was, that the predicate would refer to a set.
Yeah, well,
And then we would have a constant anyway, so. No, we want a set, so we want a constant, and that constant is going to be interpreted as a set of things, except the things inside are those weird non-set-like atom things. But you have to remember, this is what you do all the time. Nobody, I dare say, okay, let's say outside this class for the moment, really thinks of a real number as a set. Usually as a sort of an atom that lives inside the set of real numbers. So thinking of points in a set as not really sets themselves, that's nothing new. Except now we formalize it by saying we have something that points to all the atomy things, but those are the only atom things that we will be talking about. So we still have the empty set, and we can still do all kinds of things with its power set and its power set and its power set, and I'll come back to that in a moment. So the extensionality axiom simply says we still have extensionality, but for sets only. And there's hardly any moment where you have to prove something about an atom. And so the same thing we do have a version of the axiom. Yes?
I was just wondering, do we know anything about how equality behaves with atoms?
Pardon?
Do we know anything about how equality behaves with atoms? Because previously it was kind of extensionality that told us kind of what equality meant, but now we don't really know what it means for two atoms to be equal anymore.
Well,
maybe there's a problem.
No, the atoms are, I would say by definition, all distinct. We could have a set that consists of just one atom. Later, when we're going to construct models, we're going to say, well, we have our set of atoms and it is infinite. And that just means we have infinitely many things, we call them atoms, and we assume they are distinct. But like I said, it's hardly ever necessary to look at an individual atom and its properties. That never comes into play. They're just there. And we can take them, we can switch them around and everything, because the permutations will be of the atoms. But what they are, we leave that hanging. Regularity, again, is basically only for sets. I think the parentheses are in balance. So regularity simply means we have regularity for all the non-atoms. So you could stick A in here. A does have elements, and just take any atom. The atom has nothing inside it, and so the intersection is the empty set. And that's it. All the other axioms will remain the same.
Power set too?
Pardon?
Power set as well, because now the atoms are all subsets of every single set.
We'll get to that in a moment. Should be, I haven't thought of that bit. We can think that out later. Okay, so this is what the atoms are supposed to do. And in answer to the other, so this is the theory ZFA, and when we have choice, I'll add it explicitly. The A stands for set theory with atoms, and okido. What I will not do that today, but I'll do it later. We don't get into trouble if we actually assume all these things and add to it that A is an infinite set. Provided ZF is consistent. Because yes, ZFA is also subject to Gödel's incompleteness theorems. But if we decide, assume, agree that ZF is consistent, then we have to agree that this is consistent as well. And if you disagree that this is consistent, well, fine. Go and do something else. So we can create a situation, we can create a directed graph in the language of the beginning of the course that satisfies all the axioms and the things that I've written down here. So the A, in the directed graph model, you had the empty set. That was the one point that had no arrow coming in. Now we have many points without arrows coming in, and there is one designated point without arrows coming in that is deemed the empty set. All the other ones are the atoms. And then all the arrows emanate from the things that I've just described. Okay, I said I will try and show this if time permits, because I want to at least get through some of the simple applications of this permutation model idea before we go back to this slightly harder work of producing models for that situation. Okay. Now, what does the universe look like when we have atoms? Okay, this is in my eyes. It kind of looks like this. This is the bottom. And then it kind of looks like this. What do I mean by that? Well, we can forget about the atoms for a moment and start performing the power set operation with just the empty set. Then we get the traditional universe V built from the empty set. But we could, of course, also start to build power sets from A, and this is how it works. First thing that we do is we start with any set, and the only sets that I'm actually using will be the empty set and all of A, but I need this notation in two situations, so I'll do it for an arbitrary set A. You take a set S, you start building power sets. And the power set will be the next power set will be slightly different from what we did, what we used to do in the original situation, where P alpha plus 1 was just this. But this answers the question, that we had a few moments ago, the atoms are not subsets of A. They're just points. If I was going to take the power set of A, then I get the singletons of the atoms, but not the atoms themselves. And I want the atoms in my universe. The reason I wrote this down for an arbitrary set is because I want to do this for, like I said, two distinct ones. We iterate the power set operation along all the ordinals, and in the end, we define this class as the union of all those power sets that we create for all the ordinals. This is, I stole most of this from the book that is on the reading list at the website. It's Yes, The Axiom of Choice, which is a very nice book to have if you're interested in all that kind of thing. It's a bit old, beginning of the 70s, but many things there haven't been improved upon. Up till now, I would say. And that book is written with classes as a part of the language, so that's why I'm using this. You could write this into, you could write a formula that describes the whole thing with transfinite recursion and everything, but the class language here is easier to comprehend. So we have two classes that we want to that we really want to distinguish. That's this bit. We start with the empty set. We do the power set operation thing, and of course, if I start with the empty set, then this is always a part of that. So we don't really need to do that kind of thing. It's the kernel of our universe. It's actually the class of truly well-founded sets, and this is the okay. There's no separate letter for it. We could call the kernel K, and we are going into the core model. Let's say call it K, if I don't forget. Those are the two structures that we'll be talking about for the next few minutes. We're going to take, in the end, we're going to take something something that contains this, it contains A, but it is narrower than this. And the thing that is going to happen is that we're going to cut off so much from that universe that we lose all the possible well orders of A. All the well orders of A will live just outside the sub-universe that we're going to take. And the sub-universe still satisfies our axioms. That means from our axioms we cannot derive the well ordering theorem. We still have a rank function, by the way. We're going to need it once or twice. Just like in the normal von Neumann hierarchy, we can measure when a set appears for the first time, and that moment we call its rank. or rather, that sorry. That's going to be alpha plus 1. A set appears at a successor level, so it is a subset of that previous level, and that determines what its rank is going to be. All right. And by the way, we assumed that, almost forgot, if we assume that if we assume ZF, that's our starting theory, then the kernel models ZF again, because all the checking is done inside that kernel, and that's just what that's just the von Neumann thing. And of course, if we assume the axiom of choice, then every choice function or well order is already a member of that particular universe. So that's nothing difficult there, but I just want to mention it. And it says here ZF. It's well-founded. That's the true axiom of regularity holds there, and the true axiom of extensionality holds there. Because none of the things, all the things in the kernel are sets. Okay, how are we doing? Okay, fine. So that's step one. We give ourselves a universe with slightly more things than normal, some of those atoms. And those are the ones that we're going to play with. Those are the ones that are going to spoil the axiom of choice or the well-ordering theorem or something else. How are we going to do that? I was going to say we're going to make them indistinguishable to some extent. They will be different, but we won't be able to tell them apart. Other than that, we know they're different, but their properties are all the same. And that's done by permutations. And a permutation is just what it says. It's a bijection of a set to itself. And we are mostly interested in the permutations of the set of atoms of A. Okay? So whenever I say permutation, I implicitly mean that it's a bijection of A to itself. It's a permutation of the set of atoms. Now, if we only look at the permutations of the set A, then that's not very exciting. But we can make that permutation act on the whole universe. Okay, when I say permutation of A, I know what the image of every member of A is. That's pi A. And we use the same letter, the permutation pi. I use the same letter pi. We make a mapping from the universe to itself. like I said, still denoted pi. We postulate one fixed point. The empty set is going to be mapped to itself. And what is pi of x? That's a bit tricky because some books, when you have a function, pi with round parentheses of x could also mean the image set. But in this case, that's the same thing. The image set is actually the image of the point x under the mapping. And Gödel used to write this with two back quotes. I normally write it with square parentheses, and other books have other notations, but pi of x is simply going to be all the values of the members of x. What you would expect. I mean, if I'm permuting stuff, how do I permute a set? Well, I permute all the elements and collect those in a set again. It's a good exercise to actually show that this works by I did look at the program from I know you had epsilon induction. Well, this is epsilon recursion. There is an induction principle. If you prove something for all the members of a set, and it implies it for the set itself, then you have proven it for all the sets. Same thing. If you construct something and you construct pi of x out of the pi y's for y and x, and you give a uniform description of that, suddenly you have defined it for all the sets. And that is what happens here. So this is a recursive definition according to the element of relation. And, well, when you write down what we did, you will find that pi, it's a bijection from the universe to itself. Why is it a bijection? Well, if you take pi inverse and do this same thing, the extension is the inverse of the extension. Simple algebra, just like that. And because it's a bijection from the universe to itself, it preserves the equality relation and the element of relation both ways. And that means that all is well. Whatever you can think of is preserved under pi is actually preserved under pi. Okay, now I can tell you prove it, and then it takes maybe one side of a piece of paper to do that nicely. But I'll write down a few things that you get when you do this extension bit, because we'll be using those facts anyway later on. Well, for one thing, because I use the same letter for both the permutation and the extension, it's a bit difficult to express that when I take the extension of pi and the extension of rho and take their composition, then I might as well take the extension of the composition. In words it's easy, in symbols it's a little bit difficult. And of course, if I take the extension of the inverse of pi, I get the inverse of the extension of pi. Again, every proof of that will be by induction, will be by element of induction. I wrote down a few things. These are pretty obvious, but it's always instructive to write them out in full. If you take an unordered pair and you take the pi image of that, what you have to do is you have to take the pi image of the members. Well, there you go. And then once you know this, you also know this for ordered pairs. Okay. Many of the things that I'm saying here, you should check later tonight, on the way home in the train, whatever, because it's very instructive to do that. Just write out a few of those things to see what's going on, and you'll get a feeling for what's happening. When I learned this stuff, that's exactly what I did. I said, okay, let's write down what pi of f is. So for example, what would be the domain of pi of f? Pi of the domain of f write down what pi of f is, and you'll see. Pi of f is take the pi of all the members of f. Well, we just calculated what the pi of an ordered pair is. It's the ordered pair of the images. Well, there we go. And then we have to do that for all the members of f. And so now you get something like this. That looks pretty impressive, I would say. But this is the kind of thing that you expect to see when you do arguments like in those permutation models. You take a function, you permute it using some special permutation, and then you have to know what that thing does to the things in its domain. And so, okay, well, that's what's going on, apparently. To some extent, so if no, this is stretching the notation a little bit, but if you want to know what pi of f is, it's this. x is pi inverse of pi of x. So what it says here is that if I take pi of f and apply it to pi of x, what do I get? I get pi of f of pi inverse of this thing. And that goes for all the points in the domain, so that means that pi of f is pi inverse f pi, read from first to last. So what pi does basically is conjugation. If you really want to impress outsiders, you write something like this. Because apparently, if I take pi, then I conjugate it with I take its conjugation with itself, and that's pi itself. And like I said, some people will start to doubt your sanity now, but that's fine. They don't know what we know. But again, to get a feeling for what is going on, you could do some of these outlandish things and say, well, what happens if I stick pi itself into a permutation? Well, apparently it's just conjugation in the permutation. I'm going to use the letter k later for subgroups, so maybe it's not a good idea. But okay, still k is the kernel. If x is in the kernel, then pi of x is just x. Because we started out with pi empty being empty, and we don't use anything from A when we climb up the hierarchy that's the kernel. We simply keep everything in its place. Which is useful to know, because we will be starting to make those permutation models maybe in the next hour. And the kernel has a special place in that model. Those elements are always stable under every permutation, so they're symmetric, as we will call them. In general, if you have some set theoretic formula with its free variables among x1, 2, 3, 4, and so on, or you could say, I have a formula and these are substituted for the free variables, depending on your point of view, then the formula holds for this tuple x1 up to xn, if and only if it holds for the permuted tuple, and I don't mean interchange the order of the tuple things, but apply pi to them. The proof of that starts here. And then you prove it, for those who know, by induction on the complexity of the formula. If it holds for two simple formulas, then it holds for the formulas with an and or an or an arrow in between. And if you stick a quantifier in there, then it'll work as well. And so on. I mean, that's how you prove a thing like that. So basically, whatever we have and we stick it in a permutation, it will remain valid. Again, that is something that we're going to be using when we actually try and use those models later on. Well, and so on. So I'm tempted to write down some of those proofs, but I won't, because I want you to try and do them yourselves. I might even, I haven't finished the homework yet, but I'll do that tonight. I might even put one or two on the homework just to force you to do it. Doesn't mean that it's difficult, but I just want you to do it. To get the practice. Okay, so how are we doing for time? Well, this is actually a good moment to have a short break, because then we can start talking about symmetry afterwards. So satisfy your caffeine needs or whatever. We'll resume